Welcome in .Cool. For over a century, quantum tunneling has baffled scientists, a process where particles like electrons defy the odds and cross energy barriers they shouldn't be able to. While we knew the start and end points, what happened in the middle remained a mystery. But now, a breakthrough study by Pohang University and the Max Planck Institute has finally captured what goes on inside the barrier, offering new insights into this strange phenomenon. Their findings, published in Physical Review Letters, reshape our understanding of tunneling and open doors for advancements in quantum tech. Keep watching this video to learn more about this topic. The Discovery Hour event led by Professor Dong Eon Kim of Postech, the research team set out to answer a simple but elusive question. What do electrons do while inside a tunneling barrier? To find out, they used ultra-intense, ultras laser pulses to trigger tunneling in atoms. These pulses allowed them to observe electron dynamics at time scales previously impossible to capture. By analyzing the trajectories of electrons under these conditions, the team was able to see details that had remained inaccessible for decades. Their results revealed a surprising behavior. Rather than smoothly passing through the barrier, electrons were observed to collide with the atomic nucleus while still under the barrier. This interaction, which the researchers named under the barrier recollision UBR, adds a new layer to our understanding of tunneling. This finding challenges a conventional view of tunneling as a simple pass-through process. Previous models assumed meaningful interactions with the nucleus only occurred after the electron had emerged on the other side. UBR shows that the tunneling process itself is more active and complex. The study also found that electrons gain additional energy during this recollision. This boosts a process called Freeman resonance, a type of ionization where electrons become more likely to escape their atomic bonds. Remarkably, the enhancement in ionization efficiency occurred largely independently of the laser field's intensity, a result that contradicts earlier theoretical predictions and adds nuance to how strong field ionization is understood. Together, these results provide the first direct experimental insight into what happens inside a tunneling barrier. Rather than a passive crossing, tunneling emerges as a dynamic process shaped by previously hidden interactions. Scientific importance and theories this discovery addresses a century-old question and reframes how scientists model one of the most fundamental processes in quantum physics. Until now, tunneling was often described using simplified models such as a quasi-static approximation, which treated the process as field-dependent and largely devoid of complex internal dynamics. Under the barrier recollision appends that picture, revealing that electrons actively engage with the nucleus while still under the barrier, gaining energy in the process. This insight is particularly significant for strong field physics where intense lasers are used to study electron behavior. The discovery that ionization efficiency can increase through UBR and remain relatively unaffected by changes in laser intensity challenges long-standing assumptions about how tunneling behaves in high-field environments. The results also have implications for attosecond science, which explores electron motion on billionth of a second timescales. UBR opens new possibilities of controlling and measuring these ultra processes, enabling experiments that probe tunneling with unprecedented detail. By demonstrating that tunneling is not a simple one-way passage but a dynamic interaction, this research provides a new framework for refining quantum models. Future theories will need to account for UBR and its influence on ionization dynamics, resonance effects, and energy transfer. In short, this isn't just a small adjustment to existing models. It's a conceptual shift that compels researchers to revisit core assumptions about tunneling, how it happens, how it can be controlled, and how it impacts the systems where it plays a role. Implications and what's next. The implications of understanding under the barrier dynamics reach across multiple fields of science and technology. In semiconductor design, tunneling is a key mechanism in devices like transistors and diodes with deeper knowledge of electron behavior inside the barrier. Engineers may find new ways to optimize device performance, reduce energy losses, and push the boundaries of miniaturization. In quantum computing, tunneling affects the stability and coherence of qubits. Improved control over tunneling dynamics could help mitigate error rates and lead to more reliable quantum systems. For ultras laser applications, the ability to manipulate tunneling processes could enhance the generation of high harmonic frequencies, improving imaging and spectroscopy tools that operate at atomic and molecular scales. This could transform how we study matter in physics, chemistry, and material science. The findings may also inform nuclear fusion research. Tunneling plays a role in fusion reactions, and understanding under the barrier interactions could lead to better model for particle behavior in plasma environments. Looking ahead, researchers aim to explore whether UBR occurs in more complex systems such as molecules or solids, and how it can be harnessed for practical applications. These questions are likely to drive a new generation of experiments focused on expanding our control over tunneling in diverse environments. As Professor Kim noted, the study provides a pathway for understanding tunneling more deeply and controlling it as we wish. It represents not just a step forward in quantum physics, but a platform for innovation in technologies that depend on precise control of electron behavior. Outro quantum tunneling has always been a strange phenomenon where particles cross boundaries they shouldn't. A groundbreaking study now reveals that electrons interact with their environment while tunneling, offering the first glimpse into what happens inside the barrier. This discovery not only solves a century-old mystery, but also paved the way for refining these models and advancing technologies like semiconductors and quantum computers. Curious? Dive into the quantum world. Thanks for watching. Core.